Hello everyone. We all know from the i3 reports that concrete cracks are the single biggest cause of our product downgrades. One of the major causes of concrete cracks is the lack of concrete curing or applying the wrong steam curing profile. So I recorded this tutorial video to show factory managers how to use the application tool I developed to draw a concrete steam curing profile that complied with the standard. You know, it is very hard to develop a concrete steam curing profile manually because there are many variables to juggle around with. With this automated spreadsheet, you can select and change the data and variable related to your site area and product and produce the graphs of steam curing profile with a click of a button. Eliminating concrete cracks will help your site not only achieve the manufacturing cost reduction initiative by reducing downgrades, but minimize repair, rework, and customer complaints.
The steam curing profile graph looks like this chart. The temperature on the y-axis and the time on the x-axis. There are three figures that you need to know. The ambient temperature, and in this chart 20 Celsius. The time of mixing the last batch of concrete, and in this chart is 6:30 a.m. and the maximum heating temperature, and in this chart about 65 Celsius. And as you see, the time is 24 hours from 6:30 a.m. to 6 a.m. The concrete steam curing cycle is divided into 4 stages: the initial preset stage, the heating stage, the sustained temperature stage, and the cooling stage. I emailed this Excel file to the Concrete National Manufacturing team. I will first show you how to use it, and then I will explain what the probable damages to the product quality when selecting figures outside the standard limit. When you open the Excel file, you will see on the left a table showing the record of the temperature log for a 24 hours duration. There are 3 columns for a maximum of 3 cycles, and on the right of the table is the steam curing chart, and at the top is the panel where you enter the data to generate the steam curing profile. I will now zoom in into the data panel to show you how to complete the data entry. Starting from the left, the first data to enter is the time of mixing the last concrete batch. This is the cycle starting time. So for this example, if we assume it is 7 a.m., then you should be planning to get the product demold at an hour before or half an hour before. I will make it 7. In the next box, you enter the ambient temperature. Let's assume the temperature in the morning on the day you are pouring is 15 Celsius. So I enter 15 Celsius. Next, you enter the strip and cleaning mold period, and I will leave it at half an hour in this example. The following cells, you enter the maximum heating temperature. The maximum temperature recommended is 65 Celsius, so I'll make it 65. Next, the initial preset period. This is the time from 7 a.m. the start of the cycle. Let's assume it is 1.5 an hour. You will notice sometimes when you enter some of the data, a prompt box pops up to either warn you if you exceed the standard limit or give you a guideline. If you hover your mouse over some of the other cells, a yellow box pops up with description of the box. The following box in blue is the first curing cycle period time. You don't enter any data here. This figure is generated when you click on any of the update buttons. Next, the rate of heating. This is the rate of temperature increment from ambient temperature to the maximum temperature. In this example, it is from 15 Celsius to 65 Celsius. The recommended rate of heating should be between 20 to 22 Celsius, but it should not exceed 24 Celsius. I will select here 24 Celsius in this example. Next, the heating period in blue will be generated for you once you click on the update button again. The sustained period of the maximum temperature is the time you hold the maximum temperature. It is recommended to be between 2 to 6 hours. I will make it in this example 4 hours. In the next cell, you enter the difference between the ambient temperature and the temperature when you are willing to demold the product. This could be 0 Celsius if you want to cool the product to near ambient temperature for a single cast steam curing cycle, or maybe 30 Celsius for a small product in a hot weather condition if you want to do triple steam curing cycle. But in this situation, you should recover the product, recover it with the curing cover immediately after demolding to avoid thermal cracks. I will enter 20 Celsius in this example. In the next box, you enter the rate of cooling. Again, to avoid thermal cracks, you should reduce the rate of cooling. And in this example, I will select 15 Celsius. And the last blue box, first cycle cooling period, will be generated for you the figure once you click update curing profile. Now let's zoom back and click on the update curing profile. As you can see, a new steam curing profile generated for you based on the data you entered. You can see the first cycle start at 7 a.m. The program also telling us, based on the data we selected, we can have 2 cycles. Also note the second cycle cooling stage extended further down. Now I want to show you the whole screen and want to show you the print preview and how it looks like. When you click print preview, you will have 2 pages. The first page showing the temperature log, the chart with the steam profile cycles, and all the data listed at the top and at the bottom of the chart. The second page will show you the procedure and guidelines of the steam curing profile. The major consequences of the lack of proper steam curing includes increased cracking, reduced concrete strength gain, and durability problems. The initial preset stage time ranges from 1.5 hours and could take up to 3 hours, which must be increased for mixes with retardant admixture and cold weather. This period measured from the time of mixing the last batch of concrete. During this stage, the concrete begins to harden and the initial structure continues to form. The precast period allows the concrete to gain some strength before the applied heat causes differential movement within the precast concrete element and before the applied external load effect from the restraint of the mold. It also allows the concrete to develop some internal heat from the hydration process. To alleviate the lack of later strength in steam cure concrete, it is necessary to ensure adequate curing time of the concrete and use a gentle heating method to give the concrete time to form its initial structure. Generally, mixes with low water cement ratio require a shorter initial preset period. The bulkier the precast items, the longer the preset period should be. The next stage is the heating stage. The rate of heating ranges between 20 Celsius to 24 Celsius per hour. To limit the thermal damaging effect of concrete, it is necessary to use a more moderate temperature increase during the heating stage. The rate of temperature rise will depend on the setting characteristic of the cement, the shape and size of the concrete element being cured, and the mix proportions. Temperature rise must be tailored to avoid cracking and damage due to mold restraint. The temperature rise should not exceed 24 Celsius per hour with a maximum of 10 Celsius in any 20-minute period. In the heating stage, the concrete expands greatly, and in the subsequent cooling stage, the strength of the concrete cannot resist the shrinkage force, causing shrinkage cracks to form. Because the concrete is not hardened enough to resist expansion caused by steam pressure during the heating process and shrinkage caused by loss of water inside the concrete. The following stage is the sustained temperature stage. The maximum recommended concrete temperature is 65 Celsius. The time at maximum temperature should be adjusted to achieve the required strength for demolding, handling, or delivery of the precast concrete elements. A typical range is 2 hours for small elements and up to 6 hours for large elements. Strength gain from the heating operation diminishes rapidly with the maturity of the concrete. Therefore, prolonged periods of heating are neither efficient nor economical. Increasing the maximum temperature of the sustained stage over 65 Celsius increases the happening of the delayed ettringite formation, which is called DEF. DEF is the expansion of the normal product of early cement hydration, which causes cracking of concrete. Ettringite is present as a rod-like crystals in the early stage of reaction, or sometimes as a massive growths filling pores or cracks in mature concrete. Secondary ettringite forms in concrete that is heated or steam cured over 65 Celsius. Above this temperature, primary ettringite is destabilized. Subsequently, massive secondary ettringite forms. DEF may cause swelling of the hardened concrete, increase microcracking, increase the capillary porosity, reduce the cohesiveness of the cement paste, and cause debonding of the cement paste from the aggregate particles. The final stage is the cooling stage. Cooling usually takes up to 3 hours. The rate of cooling could correspond to the heating stage process. To reduce the risk of shrinkage cracking, the rate of cooling needs to be decreased. When ambient conditions are cold and product size is large, the cooling rate should be further slowed down to prevent the occurrence of the thermal cracking. During the steam curing cooling process, the surface temperature of the concrete is too high, and the surface pores coarsen due to the expansion of water and steam, causing thermal cracks to appear. The cracks occurred in the cooling stage because the concrete strength had not adequately developed to resist the shrinkage force. So in summary, the short pre-curing stage time doesn't allow the initial structure of concrete to form, which compromises concrete durability. Rapid heating causes shrinkage cracks to form. Sustained temperature over 65 Celsius leads to DEF, which causes late long-term crackings due to volume expansion causing the destruction of concrete, and rapid cooling causes thermal cracks to appear. Finally, you need to know that the stages of the curing cycle and the period for which it should be maintained depends on the following factors: grade of concrete, mix design, design life, cover to the reinforcement, mass of the element, precast element geometry, exposure conditions to which the concrete surface is to be subjected, ambient temperature, and for architectural elements, the visual requirements. In the end, I hope this tool will help your site improve high-end concrete product quality and durability by eliminating concrete thermal shrinkage and late long-term concrete cracking, and reduce repair, rework, and downgrades, and help us achieve the manufacturing cost reduction initiatives. Thanks for watching.